Okay, it's time to dive in now. Today we will present the topic is the mitochondria ATP-dependent potassium channel.
Mitrochondrial ATP control skeletal muscle structure and function.
This page introduces the members of our group. This page is the table of contents.
Mitrochondrial ATP are mitochondria membrane channel regulated potassium ion in fast space or ATP level genetic study reviews that mitochondrial muscle show mitochondria remodeling defective metabolism and improve exercise performance developmentally overexpression of mitochondria in muscle lead to mitochondria dysfunction and deficiency and severe muscle atrophy. Prefer mitochondrial ATP deletion is crucial for maintaining skeletal muscle structure and function. Objective 1. Study aim to understand how musculoskeletal structure and sensitive to the effects of subtraction is mitochondria the same as healthy cells, especially in mitochondria and metabolism change. To study all effects of mitochondria ATP gene deletion and potassium ion regulation in mitochondria in living animals.
Introduction. Excessive potassium entry can disrupt mitochondria integrity due to its impact on the electrochemical gradient. Mitochondrial ATP channel composed of mitochondria and mitosol regulate ATP-dependent potassium entry. Deleting mitochondria impair mitochondrial function and cardioprotection, while overexpressing mitochondria cause mitochondrial fragmentation and reduce membrane potential. Recent studies show mitochondrial ATP channel in skeletal muscle are crucial for mitochondrial function, affecting swelling, oxygen consumption, and muscle fatness. Overexpansion of mitochondria help study mitochondria depolarization effect on preventing death and control potassium entry, disrupt energy production, protein turnover, and autophagy leading to muscle atrophy despite active IGF-1/AKT1 signaling.
Recent experiments in mice show that deletion of the mitochondria gene in skeletal muscle led to significant change in mitochondria, including widening of mitochondria crystal and reduced mitochondrial respiration. Metabolomic analysis revealed decreased level of phospholipids, viscolipids, and cholesterol, indicating membrane remodeling and changes in muscle metabolism. Additionally, mitochondria deletion results in increased glucose metabolism in the muscle. Figure 1. Mitochondria deletion in skeletal muscle alter mitochondria crystal shape. Mitochondria deletion in skeletal muscle alter mitochondria crystal shape, metabolite profile, and respiration. The study found that mitochondria might show efficient mitochondria deletion, enlarge mitochondria crystal, and alter metabolite profile. Metabolomic revealed decreased phosphatidylcholine and release metabolite along with increased glucose 6-phosphate and release compound. Mitochondria muscle also exhibit reduced mitochondria membrane potential and lower respiratory capacity compared to control. Figure 2. Mitochondria deletion figure exercise intolerant susceptibility to demanding muscle contraction. The study investigates the impact of mitochondria deletion and overimpression on skeletal muscle. Deletion of mitochondria result in mitochondria crystal remodeling, impaired metabolism, and reduced exercise performance. Overimpression of mitochondria in muscle led to mitochondria dysfunction, swelling, and fragmentation, further contributing to muscle atrophy. The finding highlight the critical role of mitochondria in maintaining mitochondria structure and function, while in essential for muscle health and performance.
Fig 3. Skeletal muscle. Mitochondrial overexpression trigger a severe impairment. Mitochondrial overexpression impinges on skeletal muscle catabolism and stress response programs. Overexpression cause significant mitochondrial damage resulting in fragment and dysfunctional mitochondria. Pink 1. Accumulation is observed indicating mitochondrial quality control failure. Mitochondrial proteins such as TOM20 and SCOC4 are reduced, confirming mitochondrial impairment. Fig 4. Mitochondrial overexpression during adulthood triggers muscle atrophy. Mitochondrial overexpression leads to increased levels of ubiquitinate proteins LC32 and P62, reflecting impaired autophagic processes. The evaluation of these markers suggests autophagic blocks and increased cellular stress. Despite this change at the protein levels, no significant alterations in autophagy-related genes expression were detected. Fig 5. Skeletal muscle mitochondrial overexpression affects muscle mass. For weeks post-mitochondrial overexpression, there is a pronounced reduction in muscle mass in GAEDL and solid muscle. Muscle fiber size is significant decrease as confirmed through histological analysis. This finding indicates that mitochondrial overexpression induces muscle atrophy, likely different by mitochondrial dysfunctions and impaired proteins degradation.
Fig 6. Mitochondrial overexpression during adulthood trigger muscle atrophy. In adult mice, mitochondrial overexpression continue to cause muscle atrophy similar to the postnatal effect. Muscle fiber size decrease and marker of implied autophagy like P62 and LC32 are irrelevant. This suggests on protein mitochondrial dysfunction and muscle degeneration due to mitochondrial overexpansion persisting even into adulthood.
Discussion. The first, effect of mitochondrial ATP deletion. The study is the first to examine the effects of deleting mitochondrial ATP in living animals, showing significant impacts on skeletal muscles such as other mitochondrial structure and metabolisms, which impair muscle contraction and reduce exercise performance. The second, role of mitochondrial ATP in muscle force. Mitochondrial ATP is crucial for maintaining muscles for during repetitive contraction but less so for single contraction. It helps meet the energy demands of sustained muscle activity, particularly during endurance exercise. The third, effects of mitochondrial overexpression. Overexpressing mitochondria leads to mitochondrial swelling, loss of membrane potentials, and severe muscle atrophy. This is associated with disrupted autophagy and increased stress response proteins despite activated trade pathways. And the fourth, overall significance, mitochondrial ATP is vital for regulating mitochondrial function and muscle energy production. The study highlights the need for more research on mitochondrial ATP's role in muscle atrophy and its potential as a therapeutic target. Future research should explore interactions between mitochondrial ATP and other mitochondrial potassium channels.
The summary mitochondrial ATP activity regulates the volume and trap of mitochondria crystal, which impacts metabolism and energy production. Loss of ATP-dependent potassium ion regulation results in decreased muscle activity and increased sensitivity to damaging stimuli. Conversely, uncontrolled mitochondrial overexpression causes mitochondria damage and triggers cellular response associated with muscle mass loss. Future studies are needed to explore mitochondrial ATP activity in various atrophic conditions such as tissue degeneration, cachexia, or myopathies, and to investigate the interplay between mitochondrial ATP and other mitochondria potassium ion channels in different secondary of muscle function and this disease